What if everything you think you know about time is wrong? Close your eyes for a moment and picture this. You're floating in space, watching Earth from the window of a spaceship. Down on the surface, people are living their lives, clocks are ticking, days are passing, but for you, something strange is happening. Time isn't moving the same way. Minutes stretch longer, years slip by differently, and when you finally return home, you realize something impossible. You've aged less than everyone you left behind. This isn't science fiction, it's real. Time, as we experience it, isn't some universal constant ticking away the same for everyone. It's fluid, bending and warping based on where you are in the universe, how fast you're moving, even the gravity pulling at your feet. This mind-bending phenomenon is called relativistic time dilation, and it's one of the most startling consequences of Einstein's theory of relativity. Think about that for a second. Your now might not be the same as someone else's now. A second for you could be an hour for someone on a distant planet, or a fraction of a moment for a particle racing near the speed of light. It means the very fabric of reality shifts depending on your perspective. Astronauts aboard the International Space Station experience this firsthand after 6 months in orbit. They're technically a tiny fraction of a second younger than they would have been if they'd stayed on Earth. It's a small difference, but it proves something extraordinary. Time isn't absolute, it's personal. So what does this mean for us? If time is this malleable, this unpredictable, then the question, when actually are you? Takes on a whole new meaning. Are you living in the same now as someone on the other side of the galaxy? Could the past, present, and future exist simultaneously in some grand cosmic tapestry we can't yet see? These aren't just philosophical musings, they're questions cutting to the heart of how the universe works. And as we dive deeper into this mystery, you'll discover how black holes twist time into knots, how distant stars show us echoes of the past, and why your very existence might be threaded through moments that haven't even happened yet. Strap in, we're about to unravel the secrets of time itself. For centuries, time seemed simple, a steady, unchanging river flowing at the same speed for everyone, everywhere. Sir Isaac Newton imagined it as an absolute backdrop to the universe, ticking away uniformly whether you were standing still or racing across the stars. This idea felt so obvious that no one questioned it, until a young patent clerk named Albert Einstein turned everything upside down, his groundbreaking insight. Time isn't a rigid ruler measuring the cosmos, it's more like a stretchy fabric, warped by speed and gravity. Picture two identical clocks placed in different parts of the universe. One sits on Earth, ticking away as usual. The other hurtles through space at incredible speeds or orbits near a massive black hole. According to Einstein, those clocks wouldn't stay synchronized. The faster you move or the stronger gravity's grip, the slower time flows for you. This isn't some abstract theory, it's happening right now, right above our heads. The GPS satellites guiding your phone's navigation have to account for this effect every second, because they're orbiting Earth at high speeds and experiencing weaker gravity. Their onboard clocks tick about 38 microseconds faster each day than clocks on the ground. Without constant corrections, your GPS would be off by miles within minutes. So why does time bend this way? Think of the universe as a trampoline. Place a heavy object like a bowling ball in the center, and the fabric stretches downward. Now roll a marble near the edge. It'll spiral toward the dent created by the bowling ball. In this analogy, the bowling ball is a massive object like Earth or a star, and the marble is a beam of light or even time itself. The steeper the dent, the more time slows down. That's why time crawls near a black hole's unimaginable gravity but speeds up in the quiet emptiness of deep space. Suddenly, the phrase "time flies" takes on a cosmic significance. It literally does, depending on where you are. This revelation shatters the illusion that time is some universal metronome. Your now might be someone else's then or later, all depending on motion and gravity. It means the past, present, and future aren't fixed points but fluid experiences, woven together by the strange geometry of spacetime itself. And if that doesn't make your head spin, consider this. Every time you climb a flight of stairs, time runs slightly faster for your head than it does for your feet, thanks to gravity's ever so slight difference over that tiny distance. The universe is playing tricks on us, and Einstein was the first to crack the code. Einstein's special relativity begins with a deceptively simple question: what happens if you chase a beam of light? Picture standing on a train moving at half-light speed, shining a flashlight forward. Common sense says the light should streak ahead at 1.5 times its normal speed. But here's the twist: no matter how fast you're moving, light always races away from you at the same constant speed, about 1,086,000,000 kilometers per hour. This bizarre fact forced Einstein to realize that space and time couldn't be fixed. Instead, they stretch and compress to keep light's speed absolute, warping reality itself in the process. Take two identical clocks. One stays on a platform while the other boards a near light-speed train. To someone watching from the platform, the moving clock ticks slower. It's not broken. Time itself has literally stretched for the speeding clock. This happens because at extreme velocities, space and time trade places. The faster an object moves through space, the slower it moves through time. Astronauts don't notice this slowdown. Their experience feels normal, but upon returning to Earth, they'd find everyone else slightly older. This twin paradox isn't hypothetical. Atomic clocks flown on jets in the 1970s proved it, ticking nanoseconds behind ground-based ones. Why does this happen? Imagine spacetime as a flexible grid. Movement distorts this grid, forcing time to compensate. The closer you get to light speed, the more your motion through space eats into your motion through time. At 99.9% light speed, a ship's clock might tick just once while Earth's ticks 44 times. This isn't mechanical lag, it's the universe enforcing its ultimate speed limit. Nothing with mass can reach light speed because at that velocity, time would stop entirely, freezing the traveler in a single eternal moment. Now picture two lightning strikes hitting a moving train's front and back. To someone on the platform, they appear simultaneous, but to a passenger seated perfectly in the middle, the forward strike seems to happen first, because the train's motion carries them toward that flash while away from the rear one. This proves simultaneity is relative. There's no universal now that everyone agrees on. Your perception hinges entirely on your state of motion. The implications are staggering. A star exploding 10,000 light-years away might be ancient history for Earth, but for a spaceship racing toward it at near light speed, the explosion could lie in their future. Their high velocity compresses the distance and the elapsed time from their perspective. This reshapes how we view cause and effect across the cosmos. Special relativity isn't just about fast-moving objects, it's the revelation that reality is a mosaic of perspectives, each equally valid, stitching together a universe far stranger than Newton ever dreamed. Let's take Einstein's theory to its most personal extreme. What happens when time dilation affects not just clocks but people? Enter the twin paradox, one of relativity's most mesmerizing thought experiments. Imagine identical twins. One boards a spaceship bound for Alpha Centauri, 4.37 light-years away, while the other stays on Earth. The traveling twin accelerates to 90% the speed of light, making the round trip in what feels like just under 10 years for them. But back on Earth, their sibling has aged far more. Over 20 years have passed. When they reunite, the astronaut twin is biologically a decade younger than their Earth-bound counterpart. Crunching the numbers reveals just how dramatic this effect becomes. At 99.9% light speed, a 5-year trip for the astronaut would mean over 110 years have flown by at home. The equations behind this aren't just abstract math, they're the universe's recipe for time itself. Lorentz factor, the key to these calculations, shows how time stretches like taffy as velocity increases. Even at the speeds of today's spacecraft, the effect is minuscule but measurable. An astronaut spending a year on the International Space Station returns home about 0.007 seconds younger than if they'd stayed grounded. But here's where it gets paradoxically twisted. If motion is relative, why doesn't the traveling twin see Earth's clocks as the slow ones? The answer lies in acceleration. The astronaut's ship must turn around to return home, breaking the symmetry of constant motion. This jolt, whether from engines or gravity, is what ultimately stamps their journey as the moving frame, cementing their place as the younger twin. This isn't just hypothetical. Atomic clocks flown around the world in jets have confirmed these fractional age differences. And if we ever build ships capable of near light speeds, human explorers could return to find centuries have passed on Earth. The twin paradox isn't just a quirky thought experiment, it's a visceral reminder that time isn't just something we measure. It's something we live, and relativity dictates we might live it at wildly different rates. So next time you glance at a clock, consider this. Your second isn't just ticking, it's bending, stretching, and warping based on how you move through the universe. And somewhere out there, a hypothetical twin might be aging slower, proving that time, in the end, is never truly shared. Gravity's grip on time is even stranger than its pull on objects. Think about this: your feet age slightly slower than your head. That's because the closer you are to Earth's center, where gravity is stronger, the more time drags. It's a minuscule effect, sure, but measurable. Atomic clocks placed at different elevations prove it. One at sea level ticks slower than its twin on a mountain, falling behind by a few billionths of a second each year. This isn't some quirk of machinery, it's space-time itself bending under Earth's weight, warping the very flow of time. Now scale that up to something truly massive like a black hole. Near its event horizon, gravity is so intense that time doesn't just slow, it practically stands still. Picture an astronaut hovering near the edge, sending pulses of light back to a distant observer. From the outsider's perspective, each pulse takes longer and longer to arrive, stretching seconds into years. The astronaut's movements become glacial, their signals reddening as light struggles to escape gravity's grip. To someone watching from afar, the astronaut appears frozen, as if time itself has stopped. Yet for the astronaut, everything feels normal until tidal forces, complicate things. This warping isn't just theoretical. We've seen it with our own eyes, or rather, through telescopes. Light from stars skimming near the sun bends slightly, a phenomenon called gravitational lensing. But it's not just light's path that curves, time does too. GPS satellites orbit high enough that Earth's gravity weakens slightly, making their clocks tick about 45 microseconds faster per day than ground-based ones. Engineers have to account for this, blending Einstein's math with everyday technology. Without relativity, your smartphone's maps would guide you into a lake. The real mind bender, time doesn't just bend, it's stitched into space, forming a four-dimensional fabric. Massive objects dent this fabric like a bowling ball on a trampoline. Roll a marble nearby and it spirals inward, not because of some invisible force, but because the surface itself is curved. That's gravity. And just as the marble's path changes, so does time's flow around the dent. A clock placed near the depression ticks slower than one on flat fabric, proving that time and space are two sides of the same cosmic coin. So next time you check your watch, remember, it's not just counting seconds, it's tracing the invisible contours of spacetime itself, shaped by every star, planet, and black hole in the universe. Gravity isn't just pulling you down, it's pulling time along with it. At the edge of a black hole, time doesn't just slow down, it unravels. Picture an astronaut drifting toward the event horizon, that point of no return where gravity's pull becomes unstoppable. To someone watching from a safe distance, the astronaut's movements would stretch into agonizing slowness. Their final approach, which might feel like minutes to them, could span centuries, even millennia, for observers far away. Light from their spacesuit would redden, dim, and eventually fade as the black hole's gravity stretches each photon into oblivion. Long after civilizations rise and fall on distant worlds, that astronaut's last signal would still be creeping toward the universe, a ghostly echo of a moment frozen in time. This isn't just theory. The movie Interstellar brought this chilling reality to life with Miller's planet, a world orbiting so close to a black hole that 1 hour there equals 7 years back on Earth. The scene where the crew returns to their ship only to find their colleague has aged decades, that's rooted in real physics. Near a black hole's event horizon, spacetime contorts so severely that time nearly grinds to a halt relative to the rest of the universe. The numbers behind this are staggering for a black hole with 10 times the sun's mass. Just an hour at its edge could equate to over 1 million years passing elsewhere. But here's the twist: the astronaut crossing the event horizon wouldn't feel time slowing down. For them, everything would seem normal until gravity's tidal forces took over. This disconnect between experience and observation is what makes black holes so paradoxical. They're cosmic time machines warping reality so drastically that the simple question, "What time is it?" has no single answer. What's even wilder, this time dilation isn't unique to black holes. It happens around any massive object, just on a smaller scale. Earth's gravity slows time enough that GPS satellites have to adjust their clocks. But a black hole cranks this effect to extremes, bending the fabric of spacetime until the very idea of now shatters. So next time you check the clock, remember, somewhere in the cosmos, time might be flowing at a completely different rhythm, stretched thin by gravity's invisible hand. The universe isn't just vast, it's a patchwork of moments, each ticking to its own elusive beat. Imagine standing on the surface of a neutron star, a city-sized object so dense that a teaspoon of its material weighs 1 billion tons. Here, gravity isn't just strong, it's a cosmic vise squeezing time itself. A clock on this star's surface would tick half as fast as one floating in deep space. That means if you could survive the crushing forces and magnetic fields strong enough to rip atoms apart, you'd age twice as slowly as someone back on Earth. But neutron stars are just the beginning. Travel out into the vast emptiness between galaxies where gravity's grip fades to a whisper and time speeds up, clocks their tick ever so slightly faster than in our Milky Way neighborhood. Now rewind the cosmic clock further to the moments just after the Big Bang. The universe was a seething, dense soup of energy, and time didn't flow the way we know it today. In those first fractions of a second, the laws of physics as we understand them barely applied. Time itself may have flickered like a candle in the wind, stretched and compressed by the universe's violent birth pangs. This is cosmological time dilation, the idea that time didn't just begin with the Big Bang. Its very nature was different, warped by the extreme conditions of the early cosmos. Consider a photon left over from the Big Bang, now part of the cosmic microwave background radiation. That photon has been traveling for 13.8 billion years, but from its perspective, thanks to relativity, no time has passed at all. At light speed, time ceases to exist. Meanwhile, planets orbiting pulsars ultra-dense, rapidly spinning neutron stars experience time so distorted that their orbits can be predicted only by accounting for Einstein's equations. Even Earth isn't immune. Our planet's gravity well means time on the surface ticks slower than in the Moon's orbit, where Apollo astronauts left behind mirrors we still use to measure this subtle drift. The universe, it turns out, isn't just a collection of places, it's a tapestry of times, each region ticking to its own rhythm. From the frozen moments near black holes to the hyper-speed flow of intergalactic voids, time isn't just a universal constant, it's a cosmic variable, bending to the whims of gravity, motion, and even the birth of reality itself. So the next time you complain about a slow day, remember, somewhere out there, time might be racing or barely moving at all. Just when you thought relativity made time confusing enough, quantum mechanics crashes the party with rules so bizarre they make black holes seem predictable. At the subatomic level, particles don't just bend time, they shatter it. Take the infamous double-slit experiment. Fire electrons at a barrier with two openings, and they don't choose one path or the other. Instead, they take both paths simultaneously, existing in a blur of possibilities until measured. This isn't just about space, it suggests particles can occupy multiple moments at once, like a single note stretched across an entire symphony. Enter the delayed choice quantum eraser experiment, a head-spinning twist on this idea. Scientists can set up an experiment where a particle's decision to act like a wave or particle today gets influenced by a choice made tomorrow. Imagine flipping a coin, but the outcome changes based on something you haven't done yet. It's as if quantum particles receive memos from the future, blurring the line between cause and effect. In one version of this experiment, photons seem to know whether their paths would later be observed or erased, adjusting their behavior retroactively. Time in the quantum realm isn't a straight line, it's a tangled web where past and future whisper to each other. This gets even stranger when you consider quantum superposition, the idea that a particle can exist in multiple states until observed. A single electron might spin both clockwise and counterclockwise, a cosmic Schrödinger's cat of motion. Apply this to time, and you get particles existing in a haze of whens, their histories unresolved until measured. Some interpretations suggest reality branches endlessly, with every possible timeline playing out somewhere in the multiverse. Yet for all its weirdness, quantum time isn't just theoretical fantasy. Superconducting qubits in today's quantum computers leverage superposition to perform calculations at speeds impossible for classical machines. Even your smartphone's silicon chips rely on quantum tunneling, where electrons teleport through barriers, a process that defies classical notions of time and motion. So what does this mean for our understanding of now? If particles can straddle multiple moments, if the future can tweak the past, then time might not flow at all. Instead, it could emerge from deeper, timeless quantum relationships like a movie assembled frame by frame, where the frames exist all at once. The universe, it seems, keeps its secrets written in disappearing ink, with time itself as the ultimate illusion. Why does time have a direction at all? Every other law of physics works perfectly fine running backward, drop a ball, and Newton's equations describe its fall just as easily as its rise. Yet when you watch a shattered glass reassemble itself or a melted ice cube refreeze, something feels off. That's because time has a secret ingredient, entropy, the universe's measure of disorder. Unlike gravity or electromagnetism, entropy only ever increases, carving an irreversible arrow through reality. Picture a deck of cards fresh from the box, neat, ordered, low entropy. Shuffle it and chaos creeps in. The deck won't spontaneously reorganize itself, no matter how long you wait. That's entropy in action. Now scale that up to cosmic proportions. The early universe was like that pristine deck, a hot, dense, ultra-ordered state after the Big Bang. But as it expanded, entropy ballooned, scattering energy into disorder. Stars formed, burned out, galaxies spun apart, all riding this one-way slide toward chaos. Here's the twist: nothing in physics stops time from flowing backward. The equations allow it, so why don't we remember tomorrow or see broken teacups leap back onto tables? Enter Ludwig Boltzmann, the 19th century physicist who first linked entropy to time's arrow. He proposed a haunting idea. If the universe lasts long enough, random fluctuations could locally reverse entropy. Imagine walking through a vast desert and stumbling upon a perfectly sculpted sandcastle. That's a Boltzmann brain, a self-aware bundle of atoms temporarily defying entropy's tide. By sheer chance, your consciousness could be one of these flukes, hallucinating an ordered past in an otherwise chaotic cosmos. Modern physics offers less unsettling answers. Quantum gravity theories suggest the Big Bang's extreme low entropy state set the initial condition for time's arrow. Others propose parallel universes where entropy flows differently, or that time's direction emerges from quantum entanglement's web. Even black holes play a role. Their insatiable swallowing of matter may fuel entropy's relentless rise. Yet the mystery lingers. If time's flow is just statistics, could a far future universe so vast and cold that entropy appears to reverse fool its inhabitants into thinking time runs backward? The equations allow it, but for now, we're stuck with a universe where coffee cools, memories form, and time marches stubbornly forward, one irreversible moment at a time. Think about the last time you scrolled through old photos. Those frozen moments feel real, almost tangible, yet they're gone forever. Or are they? Philosophers and physicists have been locked in a quiet battle over this very question. Does only the present truly exist, or is the past, present, and future equally real, like frames in a cosmic film reel? This debate splits into two gripping worldviews, presentism and eternalism, and the answer might rewrite how you see reality itself. Presentism argues that only the now is real. The past is just a memory, the future a possibility, and everything else is an illusion. If you've ever felt like time is slipping through your fingers, this view resonates. It's intuitive. After all, you can't reach back and grab yesterday any more than you can step into next week. But eternalism paints a radically different picture. Here, time is more like a sprawling landscape where every moment from the Big Bang to the heat death of the universe exists simultaneously. Your birth, your first heartbreak, the last sunset you'll ever see, they're all out there, fixed in the cosmic fabric like stars in the sky. Relativity throws gasoline on this philosophical fire. Einstein's block universe theory suggests that spacetime isn't a flowing river but a static, four-dimensional loaf where every event sits like a slice of bread. From this perspective, the distinction between past, present, and future is just an illusion of perspective, like calling one point on a map here while standing on it. A supernova exploding a million light-years away might be ancient history for us, but for a spaceship racing toward it at near light speed, that explosion could be happening in there now. Relativity doesn't just allow for eternalism, it practically demands it. Yet presentism fights back. Quantum mechanics, with its emphasis on observation and collapse, suggests reality might only concretize in the present moment. Some interpretations argue that the universe literally computes itself forward, assembling time piece by piece like a cosmic printer. And then there's the visceral human experience, the undeniable feeling that the past is gone and the future isn't here yet. Eternalism might be elegant math, but does it explain why we grieve lost moments or ache for what's to come? The stakes here aren't just academic. If eternalism is true, then your life isn't a story being written, it's a sculpture, already complete, waiting to be discovered. Free will starts to look like a cosmic script where every choice was always destined. Presentism, on the other hand, keeps the future open, a canvas still wet with possibility. But there's a haunting third option. Maybe both views are slices of a deeper truth. Just as light is both particle and wave, time might be both flowing and fixed depending on how and where you look. So the next time you check your watch, ask yourself, are you catching a fleeting moment before it vanishes, or are you simply turning the page of a book where every chapter already exists? The answer might depend on whether you're thinking like a philosopher in the present or a physicist in the block universe. Picture the universe as a vast, dark ocean, and you're floating at its center holding a flashlight. When you switch it on, the beam spreads outward at the speed of light, illuminating a growing sphere around you. This is your past light cone, the region of spacetime where light or any signal has had enough time to reach you since the moment you turned it on. Everything outside that cone, it's invisible, unknowable, as if it doesn't exist yet. And here's the kicker, every observer in the universe has their own light cone, their own personal sphere of reality. Now point a telescope at a galaxy 10 billion light-years away. The light hitting your eyes tonight left that galaxy when the universe was in its infancy. You're not seeing the galaxy as it is now, you're seeing a fossil, a ghost of its ancient self. In fact, that galaxy might have burned out, collided with another, or been swallowed by a black hole billions of years ago. But because the light from those events hasn't reached us yet, they're literally outside our cosmic awareness. The galaxies now is a mystery, locked behind the ultimate speed limit of causality. This isn't just about distance, it's about time's stubborn refusal to sync up across the universe. Two events might seem simultaneous to you, but a fast-moving astronaut could swear one happened before the other. That's why light cones tilt and warp based on motion. Imagine drawing a cone on a sheet of paper, then sliding that paper diagonally. The cone leans, stretching toward your future or past depending on how you move. In spacetime, your light cone defines what you can influence your future cone, and what can influence you your past cone. The rest, it's a no-man's land of elsewhere, where events can't touch you and you can't touch them. Here's where it gets eerie. The Andromeda Galaxy, our nearest galactic neighbor, lies 2.5 million light-years away. If aliens there pointed a telescope at Earth right now, they wouldn't see cities or highways, they'd glimpse early humans carving stone tools. And if a supernova exploded in Andromeda today, we wouldn't know for 2.5 million years. Our light cones haven't intersected yet. In a very real sense, that explosion hasn't happened for us. The present isn't a universal truth, it's a patchwork quilt of disconnected moments stitched together by the finite speed of light. So next time you look up at the stars, remember, you're not just seeing space, you're peering into a cosmic hall of mirrors where every twinkle is a delayed echo of events long past. The universe doesn't have a single now, it has billions, each locked in its own private pocket of spacetime, waiting for light to bridge the gap. Two lightning bolts strike a train track. One hits the front of a passing train, the other hits the rear. To someone standing on the platform, perfectly centered between the strikes, both flashes appear simultaneous. The light from each bolt travels the same distance to reach their eyes at the exact same moment. But for a passenger sitting inside the train's middle seat, something bizarre happens. The train's motion means the passenger is rushing toward the light from the front strike while moving away from the light of the rear strike. The front flash reaches them first, followed by the rear. What the platform observer saw as simultaneous, the passenger perceives as two distinct events separated by time. This isn't an optical illusion, it's relativity in action. Spacetime diagrams help visualize why. Picture a graph where the horizontal axis represents space left to right along the track, and the vertical axis represents time upward for future events. The platform observers now is a horizontal line, both lightning strikes align on it, but the moving passengers now tilts diagonally, slicing through spacetime at an angle based on their velocity. Events that line up horizontally for the platform observer don't line up for the passenger. They're tilted now, intercepts the front strike's light cone earlier than the rear's. The implications are staggering. If you and a friend zoom past each other in spaceships, your agreement on what's happening right now unravels. A supernova explosion you see as occurring this instant might be hours in your friend's past or future, depending on their motion. Even the sequence of events isn't sacred. Under extreme relative velocities, you might see someone's birth before their parents' wedding, while another observer swears the order was reversed. This shatters our deepest intuitions about time. Simultaneity isn't just relative, it's personal, woven into the fabric of each observer's unique journey through spacetime. The universe doesn't just play favorites with clocks, it rewrites history itself moment by moment for every moving frame. What if you could stitch together two moments in time like threading a needle through fabric? Wormholes, those hypothetical cosmic shortcuts, might hold the key. Picture spacetime as a sheet of paper folded so two distant points touch. A wormhole would be the tunnel piercing through that fold, connecting them instantly. While Einstein's equations allow for these structures, there's a catch. They'd require exotic matter with negative energy to stay open, something we've never observed. Even if they exist, traversing one might be lethal. Intense tidal forces could shred anything entering, or the wormhole might snap shut the moment you step in. Imagine stepping through a doorway only for it to vanish mid-stride, leaving you stranded in an unknown era. Then there's cosmic strings, infinitely thin cracks in the universe's foundation, left over from the Big Bang. If two of these strings swept past each other at near light speed, they could warp spacetime so severely that closed time-like curves, loops in time, emerge. You'd orbit this twisted region, returning to your starting moment like a record needle stuck in a groove. The catch: these strings would weigh more than entire galaxies packed into threads thinner than an atom. Finding, let alone manipulating them, would be like trying to pluck a single hair from a galaxy's head. Enter the Alcubierre drive, a hypothetical warp bubble that contracts spacetime in front of a ship while expanding it behind, effectively surfing on a wave of distorted reality. Inside the bubble, time would flow normally while the outside universe whizzes by at superluminal speeds. The math checks out, but the energy required exceeds the total output of the sun. Even if we cracked that, there's the small matter of Hawking's chronology protection. Conjecture the idea that quantum effects would sabotage any time machine before it could be used, like cosmic antivirus software deleting paradoxes before they occur. But let's say you succeed. You step into your makeshift time machine and arrive in the past. Here's where things get messy. The grandfather paradox looms. Kill your ancestor before you're born, and you erase your own existence along with the murder. So how could the act ever happen? Some physicists argue self-consistent timelines would enforce a kind of cosmic censorship, where events adjust to prevent contradictions. Maybe your gun jams, or you miss the shot or twist of fate. You accidentally save your grandfather's life instead. Others propose branching timelines where every decision spawns a parallel universe, letting you rewrite history without erasing your own. The truth, we don't know. Time travel might lurk forever beyond our reach, trapped between mathematics and the universe's stubborn refusal to break its own rules. Or perhaps one day a clever engineer will find a loophole, and the answer to "when actually are you" will become "whenever you want to be." Until then, we're left with theories as tantalizing and fragile as soap bubbles, each glistening with possibility before popping into the void of the unknown. Time isn't just something we measure, it's something we feel, and that feeling can play tricks on us. Ever glanced at a clock and swore the second hand froze for an extra beat? That's the stopped clock illusion, a glitch in your brain's internal timing system. When you move your eyes, your brain briefly suppresses visual processing to avoid blurry images, like a camera closing its shutter between shots. But it doesn't want you noticing these gaps, so it backfills the missing moment with the first thing you see after your eyes settle. That's why the clock's second hand seems to linger. Your brain stretches perception to cover the gap, stitching time like a clumsy editor. Now imagine something far more intense, a car crash. Survivors often describe time slowing to a crawl, details sharpening as if the world switched to slow motion. This isn't relativistic time dilation, it's your brain kicking into overdrive. During trauma, the amygdala floods your system with stress hormones, turbocharging memory formation. More sensory data gets logged than usual, creating the illusion that events unfolded more slowly. Play back the memory, and it feels elongated because your brain packed in extra frames. Yet in the moment, your ability to react doesn't actually speed up. Time didn't slow, your recollection just got denser. But what if you could tweak time's dials chemically? Psychedelics like LSD shatter the brain's default timing networks. Normally, the prefrontal cortex acts as a conductor, synchronizing sensory input into a coherent timeline. Disrupt that, and seconds might stretch into eternities or cascade past in a blur. One study had participants estimate intervals while on psilocybin. Their guesses varied wildly, as if their internal metronomes were melting. Even caffeine alters perception, sharpening focus to make hours feel like minutes, while depressants like alcohol smear moments together like wet paint. The real revelation: there's no time center in the brain. Instead, perception emerges from a symphony of regions, the basal ganglia ticking like a drum machine, the parietal lobe mapping sequences, the insula weighing duration against emotion. A boring meeting and a roller coaster ride might last identical minutes, but your brain won't let you believe it. Time, in the end, isn't just a dimension. It's a story your brain tells itself, one where suspense, shock, or serotonin can rewrite the clock. Time warps differently for every living thing on Earth. Take the common housefly, those pesky insects you can never seem to swat. Their world moves in what feels like slow motion to us. A fly's eyes process light nearly 4 times faster than human eyes, meaning a second for you is a drawn-out drama for them. That's why your descending newspaper looks like it's drifting down in molasses, giving them plenty of time to dart away. Scientists call this temporal resolution, the speed at which an organism perceives changes. For a hummingbird, wings beating 80 times a second, time stretches just enough to navigate flower to flower in a blurred dance. Meanwhile, a sloth's sluggish metabolism means their perception crawls, life unfolding at half speed compared to ours. Now swing to the opposite extreme: bristlecone pines clinging to mountain slopes for 5,000 years. These gnarled ancients experienced time as a geological whisper. A single human lifetime might register as just a few growth rings in their timber. Their cells divide so slowly that decades blur into a single biological sigh. Compare that to the mayfly, which emerges from the water, flutters for a single day, and dies without ever knowing nightfall. Its entire existence is a sprint metabolism cranked to maximum, every second bursting with urgency. These insects don't just live briefly, they perceive time in hyperlapse, cramming a lifetime of sensory input into hours. Even within species, time bends. A mouse's heart races at 600 beats per minute, hurtling through years in the time it takes an elephant, whose heart plods at 30 beats, to experience one. This scaling of biological time, known as metabolic rate theory, suggests smaller creatures essentially live in fast forward. A dog's 7 years to our one isn't just folklore, it's physics. Their cellular clocks tick faster, burning bright and brief, but the real marvel: some organisms cheat time entirely. The Turritopsis jellyfish reverts to infancy when stressed, resetting its life cycle like a cosmic undo button. Tardigrades, those microscopic water bears, dehydrate into glass-like statues for centuries, then reanimate as if waking from a catnap. And in Antarctica, microbes buried in ice for millions of years stir back to life when thawed, making time itself seem optional. So the next time you check your watch, remember, your heartbeat, your breath, even the flicker of your thoughts are just one rhythm in Earth's symphony of timekeepers. From the lightning-fast blink of a dragonfly's eye to the patient unfurling of a sequoia's branches, life dances to countless metronomes, each perfectly tuned to its own slice of eternity. Ancient cultures grasped time's fluidity long before Einstein scribbled his first equation. In Hinduism, time spirals in endless cycles: creation, preservation, destruction, repeating across epochs called yugas. Each cycle lasts 4.32 million years, mirroring the cosmic scales relativity operates on. Hindu texts even describe divine years, where one day for Brahma equals 4.32 billion human years, a foreshadowing of time dilation's extreme elasticity. The gods experience reality at a stretched tempo, much like an astronaut near a black hole would perceive centuries passing in moments elsewhere. Meanwhile, Abrahamic traditions embraced linear time, an arrow shot from Genesis to Judgment Day. This view shaped Western science's hunt for time's beginning, culminating in the Big Bang theory. Yet buried in medieval Jewish mysticism are hints of temporal relativity. The Zohar describes souls in higher realms witnessing 1,000 years in one night, while Islamic scholars like Al-Ghazali pondered whether God's time flowed differently from mortals. Sound familiar? It's the twin paradox wrapped in theological robes. Then there's Australia's Aboriginal dream time, where past, present, and future weave together like threads in a tapestry. Ancestral spirits sculpted the land in a time beyond time, a dimension where events aren't chronological but eternally present. Modern physics echoes this with the block universe, where all moments coexist. When relativists say now is subjective, they're voicing what indigenous cultures knew intuitively. Time isn't a river but an ocean with currents running every which way. The Maya took precision further, their long count calendar tracking time in fractal-like bundles of days and centuries. Their astronomy revealed celestial cycles so vast, they make relativistic time dilation seem like child's play. And in China, the Taoist concept of wu-wei, flowing with time's natural rhythm, resonates with relativity's insistence that fighting spacetime's curvature is futile. What's striking isn't just that these ideas predicted Einstein. It's that they emerged without telescopes or particle accelerators, from minds deeply attuned to nature's whispers. Perhaps time's true nature isn't hidden in equations alone, but in the collective intuition of civilizations who stared at the stars and sensed the universe's elastic heartbeat. Hollywood loves playing fast and loose with time, but how much of it holds up under real physics? Take Back to the Future, the ultimate time travel romp, where Marty McFly hops between decades like skipping stones. It's thrilling, but the science, not so much. Changing the past to alter the future creates paradoxes faster than you can say, "Great Scott." Reality doesn't work like a ripple-free pond mess with one event, and the universe doesn't neatly reweave the timeline. Even worse, Doc Brown's DeLorean implies time is a fixed track you can jump between, ignoring relativity's core lesson. Time isn't a road, it's more like quicksand, shifting under every observer's feet. Now flip to Primer, a cult indie film that treats time like a physicist's puzzle. Its time machine isn't sleek, it's a clunky metal box where users endure grueling temporal loops. The film nails the gnarly side effects. Characters accidentally clone themselves, timelines tangle irreversibly, and every fix breeds new chaos. This mirrors real quantum theories where closed time-like curves could spawn infinite versions of events. While the tech remains fictional, the consequences feel eerily plausible, like a lab experiment gone wrong, where causality isn't broken so much as shredded. Then there's Arrival, which trades gadgets for linguistics. When aliens gift humanity a circular, timeless language, learning it rewires the protagonist's brain to perceive time non-linearly. Past, present, and future blur into a single vista. This taps into the Sapir-Whorf hypothesis: language shapes thought. While we've yet to find an alien tongue that cracks time's code, the film's portrayal of perception-altering knowledge isn't pure fantasy. Neurologically, our sense of time is malleable. Bilingual speakers often report feeling different when switching languages, and psychedelics can dissolve temporal boundaries entirely. Arrival just takes this idea to its cosmic extreme. Even Interstellar's time-stretched planet near Gargantua bends reality just enough to feel authentic. The movie consulted physicist Kip Thorne to ensure its black hole's time dilation matched Einstein's math. Result: every hour on Miller's planet costs 7 Earth years, a gut-wrenching twist rooted in actual general relativity. Compare that to The Flash, where time travel looks like sprinting through a glowing tunnel. Fun? Absolutely. Science? Not even close. Sci-fi's best time stories aren't the ones that ignore physics, they're the ones that wrestle with its weirdness. Whether it's Primer's messy causality or Arrival's mind-bending linguistics, the most compelling tales treat time not as a plot device, but as a character unpredictable, merciless, and utterly inhuman in its logic. So next time a movie shows someone hopping eras like stepping through a door, remember, real time travel wouldn't be a joyride. It'd be a high-stakes game with rules we're still struggling to decode. Imagine trying to schedule a call with someone halfway across the world without time zones. You'd have to say, "Let's chat at exactly 73,200 seconds past midnight Greenwich time." Utter madness. That's why we sliced Earth into 24 neat time zones, each roughly 15 degrees of longitude apart. But here's the twist: these zones are more political than scientific. China, for instance, stretches across 5 theoretical time zones but uses just one nationwide. Meanwhile, tiny Nepal sits at a quirky offset 45 minutes ahead of India, its giant neighbor. This patchwork system means timekeeping is as much about human convenience as celestial mechanics. Underpinning this global clockwork are atomic clocks, masters of precision that don't just count seconds but define them. These aren't your grandfather's pendulum clocks. Inside, cesium or rubidium atoms vibrate at mind-boggling frequencies, 9,192,631,770 times per second for cesium. That's the official heartbeat of our planet, set by the International Bureau of Weights and Measures in Paris. Miss a single vibration, you've lost a billionth of a second. These clocks are so accurate they drift by less than a second over 15 million years. Yet Earth doesn't always cooperate. Our planet's rotation wobbles, slowed by tides, sped up by seismic shifts, even influenced by melting ice caps redistributing mass. When cosmic time measured by atomic clocks and solar time based on Earth spin drift apart, we insert a leap second. Since 1972, we've added 27 of these extra ticks, like cosmic snooze buttons letting Earth catch up. Tech companies loathe them. Google smears the extra second across hours to avoid glitches, while Twitter once crashed during a leap-second apocalypse in 2012. Even with all this precision, relativity sneaks in. The GPS satellites guiding your road trip have atomic clocks too, but they tick 45 microseconds faster daily than ground-based ones. Why? They're both farther from Earth's gravity and hurtling at 14,000 kilometers per hour. Ignore Einstein's corrections and your navigation would misfire by kilometers within minutes. So next time you check the time, remember, behind that simple number hides a saga of quantum vibrations, planetary wobbles, and the silent tug of war between Earth's rotation and humanity's relentless pursuit of perfect precision. What if the entire history of the universe could fit inside a single calendar year? Picture this: a cosmic countdown where every month, every day, even every second represents millions or billions of years. On January 1st, the Big Bang ignites the universe in a blaze of energy and matter. For months, it's a slow simmer. Galaxies form in February. Our Milky Way takes shape in March. The sun flickers to life in late August. But life, that doesn't appear until September, when single-celled organisms emerge in Earth's primordial oceans. Dinosaurs don't stomp onto the scene until mid-December, ruling the planet for over 200 million years, yet in our cosmic calendar, their reign lasts just days. Then comes December 31st, the final day of the year. Early in the morning, an asteroid strikes, wiping out the dinosaurs. Mammals seize their moment, evolving rapidly through the afternoon hours. By 11:30 at night, early humans are carving tools. 11:59, agriculture begins, and in the last 10 seconds before midnight, all of recorded human history plays out. Empires rise and fall, the Renaissance blooms, the Industrial Revolution sparks. Einstein publishes his theory of relativity with just 2 seconds left on the cosmic clock. The moon landing happens barely a fraction of a second before the year ticks over. This astonishing timescale puts our existence into brutal perspective. Everything you've ever known, every person, every invention, every war and discovery occupies less than the blink of an eye in universal terms. The pyramids were built closer to our present moment than to the extinction of the dinosaurs, and the mind-bending theories that reshaped our understanding of time. They've only existed for a cosmic heartbeat, yet here's the paradox: in those final milliseconds, we've unlocked secrets about the universe's first moments. Telescopes now peer back to within seconds of the Big Bang on our cosmic calendar, while particle accelerators recreate conditions from the universe's first week. We're latecomers to the cosmic party, but we've arrived just in time to decipher the invitations written at the dawn of time itself. So the next time you feel insignificant, remember, the universe spent nearly its entire existence preparing the stage, and we get to witness the final act. Future timekeeping may not rely on Earth-bound atomic clocks at all. Imagine fleets of ultra-precise atomic clocks orbiting in deep space, far from our planet's gravitational fluctuations and atmospheric interference. These celestial timekeepers could form a network spanning the solar system, their synchronized ticks creating a cosmic internet of time. Each clock would compensate for relativistic effects based on its position and velocity, allowing spacecraft to navigate with unprecedented accuracy. The European Space Agency's ACES mission already tested this concept on the International Space Station, where an atomic clock kept time while accounting for orbital speed and Earth's gravity. Future versions might float near Lagrange points, gravitational sweet spots where stability is perfect for measuring time's subtle warping across interplanetary distances. Then there's the quantum frontier. Today's quantum computers manipulate qubits that exist in multiple states at once, but future iterations might harness time itself as a computational resource. Theoretical models suggest time crystals, structures whose atoms repeat in time rather than space, could serve as quantum memory that persists without energy input. Picture a processor where calculations unfold across multiple temporal dimensions, solving problems too complex for conventional computers by exploring countless parallel timelines simultaneously. Google and NASA's Quantum AI Lab has already demonstrated millisecond-scale coherence times in qubits. Extend that stability, and you've got a machine that doesn't just compute, but dances across the fabric of spacetime to find answers. But perhaps the most elegant solution comes from nature's own timepieces, pulsars. These spinning neutron stars beam radiation with metronomic precision, some keeping time better than atomic clocks. The NICER experiment on the ISS currently tracks millisecond pulsars, their X-ray flashes serving as cosmic lighthouses. Future spacecraft might navigate by pulsar networks, triangulating position using the minute differences in pulse arrival times across light years. Each pulsar's unique spin signature would act like a galactic IP address, allowing probes to pinpoint their location anywhere in the Milky Way without earthly references. The Voyager Golden Record even included pulsar maps as a potential locating system for extraterrestrial finders, proof that the universe itself may hold the ultimate clock. These technologies hint at a future where timekeeping isn't just about precision, but about harmonizing with the universe's own rhythms. From relativistic networks to quantum temporal engines and spinning stellar beacons, we're learning to tell time by the cosmos' heartbeat rather than forcing it into earth-bound boxes. The second hand on your watch might soon have company, a symphony of celestial cadences keeping time across the stars. What if every choice you make doesn't just alter your future, it spawns an entirely new universe? That's the spine-tingling premise of the many worlds interpretation, where reality branches endlessly like a cosmic choose-your-own-adventure book. Imagine flipping a coin: heads, you take a job offer; tails, you decline. In this view, both outcomes happen, splitting the timeline into parallel streams where each version of you lives out the consequences. But here's the twist: time doesn't just fork at decisions. Quantum events, a radioactive atom decaying or not, a photon passing through one slit or another, create new universes constantly, each with its own unique timeline. Unlike classic time travel stories where changing the past overwrites history, many worlds suggest no paradoxes because every possibility plays out somewhere. Now zoom out to an even grander scale, eternal inflation's bubbling multiverse. Picture the cosmos as a frothing sea of spacetime, where new universes constantly bud off like bubbles in boiling water. Each bubble universe cools into its own distinct reality with different physics, constants, and crucially, different flows of time. Some might have time racing forward like a river in flood, while others creep like glaciers. A few could even have time looping back on itself, or dimensions where cause and effect don't apply. The mind-bending implication, the arrow of time, we experience that relentless march from past to future, might just be a quirk of our local bubble, not a universal rule. These theories force us to rethink what now even means. If countless versions of you exist across branching timelines, is your present moment truly unique? And if bubble universes have disconnected time flows, could there be realms where dinosaurs never went extinct, or where humanity's clock hasn't even started ticking? The unsettling answer, probably, yet we're forever locked out of these alternate timelines. No DeLorean or wormhole can bridge the gap, the real kicker. This isn't science fiction. The math behind quantum mechanics and inflationary cosmology leads here naturally, even if we can't yet test it. Every time you hesitate between tea or coffee, somewhere in the multiverse, another you sips the other choice, completely unaware of the countless timelines spiraling outward from that single moment. Time isn't a straight line, it's a forest of infinite branches, each whispering a different version of what if. What if time isn't a flowing river but an illusion, a trick our minds play to make sense of a universe where nothing actually moves? Julian Barber, a physicist with a radical vision, proposes just that, a reality where time doesn't exist at all. In his timeless universe, change is the only real phenomenon, and what we call time is just a sequence of frozen moments, like frames in a cosmic film reel. Imagine every possible configuration of the universe, every arrangement of atoms, every position of stars, as a single point in a vast landscape. Barber calls these points nows, and in his view, reality isn't a journey through time but a hopscotch game between these static snapshots. Your experience of moving from morning to night, just your brain stitching together closely related nows, creating the illusion of continuity. This idea isn't just philosophical sleight of hand, it's a serious attempt to solve one of physics' biggest headaches, uniting quantum mechanics with gravity. Einstein's general relativity treats spacetime as a dynamic fabric, warped by mass and energy, but quantum mechanics, the rulebook for particles, has no place for this smooth, flowing time. At the smallest scales, time seems to vanish altogether, leaving equations where events don't unfold. They just are. Barber's timeless physics tries to bridge this gap by ditching time entirely, suggesting that the universe is fundamentally a collection of moments without past or future. Think of it like a cosmic flipbook. Each page shows a different configuration of the universe, particles here, energy there, but no page is before or after another. The sense of movement comes from how similar one page is to the next. Our brains, wired for cause and effect, interpret this similarity as the flow of time. But in reality, there's no arrow, no direction, just an endless gallery of nows. The implications are staggering. If Barber's right, then aging, decay, even the Big Bang aren't processes unfolding over time, they're patterns in the arrangement of these nows. A dying star isn't a star changing, it's a sequence of static states where the star appears in different stages of collapse. Your childhood, your present, your future, they all exist simultaneously, fixed in this cosmic mosaic. Yet this raises a thorny question. If time is an illusion, why does it feel so real? Why do we remember the past but not the future? Barber's answer lies in complexity. Some nows are highly ordered, like the low-entropy early universe, while others are chaotic, like today's scattered energy. our perception of time's flow might just be a side effect of moving from simple to complex arrangements, like watching ink disperse in water. The direction we call forward isn't time, it's entropy increasing, creating the illusion of a timeline. Not everyone's convinced. Critics argue that without time, physics loses its predictive power. How do you explain why one now follows another? But Barber's ideas gain traction in quantum gravity research, where time's role is already fuzzy. Loop quantum gravity, for instance, suggests spacetime is granular, made of tiny chunks that might not even have a temporal order at the smallest scales. So the next time you check your watch, consider this. Those ticking seconds might be no more real than the flicker of a movie projector, stitching together moments that exist eternally, waiting for your mind to animate them into a story called time. What if the flow of time isn't just something we observe, but something we create through our own awareness? This startling idea traces back to Benjamin Libet's controversial experiments in the 1980s, where he asked subjects to note the exact moment they decided to move a finger while monitoring their brain activity. The results were eerie. Brain signals predicting the movement appeared before the subjects consciously felt they'd made the decision, sometimes by hundreds of milliseconds. It was as if their brains were committing to actions before their conscious minds even got the memo. This threw a wrench into our understanding of free will, but it also hinted at something deeper. Consciousness might not ride atop the river of time, it could be shaping the river itself. Fast forward to modern neuroscience, where theories like integrated information theory propose that consciousness emerges from the brain's ability to weave together information across time. Picture your brain as a symphony conductor, blending notes from past, present, and future into a seamless experience of now. This binding of moments isn't passive, it's an active construction, stitching together sensory inputs, memories, and predictions to create the illusion of a continuous timeline. Damage certain brain regions, and this fragile unity shatters. Patients with conditions like akintopsia, motion blindness, see the world as a series of frozen snapshots, like flipping through a stack of photos instead of watching a movie. Their brains lose the ability to bind time, proving just how much our perception of flow is a neurological sleight of hand. Even stranger are the time-bending quirks of our perception. The brain constantly edits our experience, hiding its own processing delays. When you clap your hands, the sound takes milliseconds longer to reach your ears than the visual signal hits your eyes. Yet you perceive them as simultaneous, your brain backdating the sound to match the sight, rewriting history after the fact. This post-diction effect reveals that what we call the present is actually a carefully crafted illusion, a best-guess reconstruction of events that already happened. What does this mean for time itself? Some theorists argue that without consciousness, time might not flow at all. It's our awareness that gives it direction and texture. In a universe of static space-time, we could be the ones animating the frames, turning a cosmic slideshow into the lived experience of days, seasons, and lifetimes. So the next time you check your watch, remember, those ticking seconds might not just be something you measure. They might be something you make a fragile, beautiful collaboration between mind and cosmos. Every minute of every day, gravity and motion are quietly tweaking the speed at which you age, though the differences are so tiny you'd never notice without atomic clocks. Take flying, for instance. A commercial jet cruises at around 900 kilometers per hour, high enough that Earth's gravitational grip weakens slightly. According to Relativity, this means passengers experience time very marginally faster than people on the ground. Over a 5-hour flight, you'd age about 5 nanoseconds, roughly the time it takes light to travel 1.5 meters. That's less than a blink, but it's measurable. Now imagine a pilot who spends 20,000 hours in the air. Their body would technically be about 100 microseconds younger than if they'd stayed earthbound. It's not exactly the fountain of youth, but it proves time's flexibility isn't just for astronauts. Elevation plays an even stranger role. If you live in a high-rise apartment or a mountain town, you're aging faster than someone at sea level, again by fractions of a second over decades. Gravity weakens with altitude, so time speeds up the farther you are from Earth's core. The effect is minuscule but relentless. A person living in Denver, the mile-high city, would age about 100 nanoseconds per year faster than someone in Miami. Over a lifetime, that adds up to roughly 3 microseconds, enough for atomic clocks to detect, though your mirror won't show any difference. But here's the real kicker. For communities living in the Himalayas or the Andes, these tiny effects compound. Researchers studying Tibetan villagers at 4,500 meters found their cells show subtle markers of accelerated biological aging compared to lowland populations. The higher altitudes, thinner air, and increased cosmic radiation play a role, but relativity contributes too. Time literally flows faster for them, even if only by a whisper. It's as if the universe is quietly pressing the fast-forward button on their lives, 1 nanosecond at a time, yet these effects pale next to extreme scenarios. If you could live atop a skyscraper 10 kilometers tall higher than Everest, you'd age a whole millisecond faster per year. Move to a space station and the tables turn. Astronauts orbiting 400 kilometers up age slower than Earthlings, thanks to their high speed counteracting the weaker gravity. The interplay of velocity and elevation means every step you take, every flight you board, tweaks your personal timeline in ways Einstein first dreamed up over a century ago. So the next time you glance at a clock, remember, your life isn't just ticking away, it's bending, stretching, and warping in ways so subtle, only the universe's strictest laws can measure them. Time doesn't just pass, it adapts, molding itself to your place in the world, down to the very atoms in your bones. So where does all this leave us in the grand scheme of things? Your now isn't just a tick on a clock, it's a delicate dance between speed, gravity, and your place in the universe. Stand still and time flows one way. Accelerate to near light speed and it stretches like taffy. Climb a mountain and it speeds up, plunge toward a black hole and it grinds to a crawl. Even your head and feet experience time at slightly different rates, thanks to Earth's gentle gravitational gradient. The present moment isn't some universal truth, it's a personal experience shaped by how you move through the cosmos. Consider 2 astronauts orbiting Earth at different altitudes. Their high fives would never truly align because time bends differently for each of them. Or picture a star exploding in a distant galaxy for civilizations watching from other angles. That cataclysm might be ancient history unfolding now or still waiting in their future. There's no cosmic bulletin board announcing current events for everyone. Instead, the universe offers a mosaic of moments, each valid, each real, but never quite the same for any 2 observers. This isn't just physics, it's poetry written into the fabric of reality. Every heartbeat, every breath you take is your personal timestamp in space-time, a fleeting intersection of velocity and gravity's embrace. The watch on your wrist ticks to the rhythm of your journey through the cosmos, a rhythm no one else shares exactly. You're not just living in time, you're weaving it moment by moment with every step, every leap, every orbit around the sun. As Carl Sagan once reflected, we are a way for the cosmos to know itself. In this vast, elastic expanse of space-time, conscious beings like us emerge to witness time's flow, to measure its bends, to marvel at its mysteries. So the next time you pause to check the hour, remember, you're not just reading numbers on a dial, you're touching the universe's pulse, feeling the warp and weft of reality itself, a fleeting, beautiful participant in the grand story of existence.